Saxon Advanced Mathematics, not algebra, mathematics. Lesson 57. We're going to talk about some more sinusoid fun today. You guys, this lesson might be a little bit complicated at first, but you're going to enjoy it. It's about sinusoids, and it's really fun. Okay, let's review what we already know about sinusoids. Let me just show you in the book so we can go fast. Don't have to bog down in this. Okay, the basic form of a sinusoid is a curve that goes like this, right? And it repeats, goes up and down. Sinus curves, or sine curves rather, sorry. Their sinusoid describes that wave pattern. The sine curve starts at 0 and rises out when it's positive, right? And it starts at 0 and goes down when it's negative. So that's positive, negative. The amplitude is how high and low the curves max out. And we look at the center line and measure up and down in order to find that, right? Here's how we show that. If the center line was different than 0, we would have a number out in front. But that shows the amplitude. Here it is -3. The negative shows that it's going down first, and the 3 shows that it goes 3 units above and below the line. Cosine, we remember, it starts, its 0 value, it starts high, right? And then it goes down and back up. So that's a positive cosine curve. A negative cosine curve starts at the bottom and then goes up and comes down, right? So those are the 4 shapes, coming out of the 0 going up, coming out of 0 going down, starting at the maximum, starting at the minimum. Amplitudes work the very same way, 2 to -2, so we put that, the 2. This is always a positive, the amplitude itself is a positive number. The negative sign reflects to whether we're going up or down first. Okay, so the amplitude is not measuring this because it's +2 or this because it's -4. It's just saying this is down. So the minus sign we think of separately than we do the amplitude itself. Okay, now, ready? We're going to mess with you now. Imagine taking just a basic curve like this, okay? So our amplitude is 1, our center line is 0. There are our units. And imagine, don't worry about where this is on here yet. Imagine we take this basic curve and we make it out of yarn, and then we drench it in Elmer's glue and let it dry. Did you guys ever do that when you were little kids? Oh God, we used to do that in Girl Scouts. It was great fun. So now this curve, it's not glued to the paper. It's just dried so that it's hard and we can pick it up, right? We can now pick this thing up and move it back and forth where we want. And here's where we've set it down. Now I'm going to draw this picture in my book, so I want to talk about it a little bit more. This is where it gets really cool. Here's our curve. Here's our y. Here's our theta going this way. 90, 180, 270, 360. Then I'll do another one. Okay, so these are the basic quadrants, 90, 180, 270, 360. I'm not going to write those numbers in because I want to be able to show you something else. And it goes up and down 1 unit. Okay, now this is 90. So I'm going to make a special mark in here at about 45 degrees, negative. And I'm going to make another one. Oh, yes, 45 degrees here. These are important numbers, and I'll show you what they mean in just a minute. And then this is okay. Now, let me show you what's happening with this curve. It is, second, I want to make sure I draw exactly like it is in the book. Okay. All right. We have taken our sine or cosine curve. We've hardened it with Elmer's glue and we've set it down on the grid, but we didn't set it perfectly so that it was either coming up out of the zero or peaking or minusing. It's crooked. We've laid it crooked on the grid. This is called a phase shift. We have shifted the curve so that it's crossing at a different phase than we are used to seeing. Now, that's kind of interesting and kind of cool. We can account for that in the way we write the equation. The thing that's really weird is that because this shape is similar in a sine curve or a cosine curve, we can write this actual physical curve now as either sine or cosine, whichever we want. So we're going to learn how to do it both ways. If we are thinking of this as a sine curve, if we want to write this as a sine, we would write y equals the sine, and we don't have to do anything with amplitude or center line because everything's perfect. We definitely left those parts out. And what we do is we write theta in parentheses. This is how we write a phase shift. Now, if this is a sine curve, then that means we know that it's beginning. We measure it from where it crosses this line going up, right? That's what we want to normally write a sine curve as. It is 45 degrees to the negative sign. So what we write here is theta plus 45 degrees. Notice that that is the opposite sign. It's actually crossing at minus 45 degrees, but we put it in the equation as plus, okay? If we want to write this same curve as a cosine, here, I'll do it on here because I don't want to change the page. Cosine writes at the peak, we write it at the peak, right? Well, there's the peak. That's actually plus 45. So to write this as a cosine, again, we don't have to adjust amplitude or center line. They're perfectly normal. We just adjust for the phase shift. It will be theta. And then because this is a positive 45 shift, we write it as minus 45 degrees. And it's crossing at plus 45 degrees. So the sign of a phase shift is opposite. And I'm going to note that here. Sign is opposite. That's my shorthand way of saying if the place that it's coming from is minus 45, you write it as plus 45 and vice versa. That has nothing to do with sine or cosine. That just has to do with where it's crossing. All right, so that's what a phase shift is. I want you to hang on to that image of the piece of yarn making the perfect curves and then gluing it so that you can pick it up and drop it down at different points on the grid, and it will keep its same shape. It will just lay on top of the grid at different places. All right, let's do a couple more problems of those. 2 of them. And then we're going to look at one more wrinkle in, oh, I turned the wrong way. No, I didn't. Oh, look what I did. I wrote this on top of the review problem. Oh, that was crazy. Okay, so this is example. Sorry, I know I'm not in the camera here. 57.1. Okay. Write the equation of the sinusoid. Let me show you the problem. Shown here as a sine curve with a phase angle and also as a cosine curve with a phase angle. Well, that's exactly what we did there. So let's copy this down and get the picture in front of us so we can see what we're doing. And these are fun because you get to draw them, and I always enjoy that. All right, what John does in these problems that I find very helpful is, oh, he's not doing it here. He's just putting these numbers relate to the high point of the curve is 30. It crosses at 120. The low point is 210. And then it comes back up. These are not the numbers that we're used to seeing here, but these are the numbers that match to the key points of this curve. So that is very helpful. So there's our first point. There's our first quadrant. Second, third, fourth, fifth. All right. Y, this is theta. I'm going to put these numbers in. This is 30 degrees. 120. 210. We can see they're going up by 90, so that makes sense. It's the normal size quadrant. 210. 300. And that's good. And then this one is minus 60. So we can see these quadrants are the normal size. They're just not lining up perfectly, right? Because there's 90 degrees between each set of points. So I'm still looking at the picture. We are going to start here. So it's going to go up and back down and then bottom out and come back up, and so on, right? Let's look at our center line and high and low point data. The center line is 4, and then this is 6, and this is 2. Okay, so we're gonna write this sinusoid here, which is made of hardened yarn. And, whoops, that was too low. And we're going to write it as a sine curve and as a cosine curve. All right. The center line is 4. The amplitude is 2, right? From 4 to 6 and then back down to 2. 2 times, and then we're going to go sine. Oh, wait, we don't need it there. We need it here. Theta. And then it'll set up the very same way because the center line and the amplitude information is exactly the same whether you're in cosine or sine. The parenthesis does not go there. It goes next to the argument because we're going to be adjusting the argument. Okay, so now we're looking at the sine curve. We're looking at this as a sine curve. We measure it from the place where the curve crosses the axis and is headed up. So it's right here. Pretend it's perfect. Okay? That is at minus 60 degrees. We know that we flip the sign when we change the argument, so we put plus 60 degrees. That is the equation of our little gem as a sine curve. But now we're going to switch our perspective and imagine it as a cosine curve. A cosine curve we will measure from the top. So that means we are interested in 30 degrees. It's a 30 degrees phase shift. It's a positive phase shift, so we write it as a minus in our equation. Okay? Some people ask, well, how do you know it's not a minus curve? You could write it as a minus sine curve or a minus cosine curve, but normally we wouldn't want to do that. We'll just assume that we want to write it as positive. So these are the answers to this equation, or this example rather. Yay. Beautiful, right? Okay, let's do another one. Write the equation of this function as a sine curve with a phase shift. Okay, so this one we know we only want the sine version. We don't have to write the cosine version. Okay, so this time I'm not going to copy it. I'm going to show you how I would do it if I was serving it as homework. The first thing I do is I look to see what's the center line and what's the amplitude. The center line is -6. And then it goes up 1 and down 1. Okay, so I'm going to start. That's my center line. The amplitude is still 1, so I don't have to do anything weird about that. So I can just say plus the sine. We're only interested in sine. Now I know there's a phase shift, so I put the parenthesis, theta. Now I go back and look at the picture. I want the place where the curve is coming up, and I want the one that's closest to 0. So I could technically look at this and go, oh, look, it needs a phase shift. It's a positive 270, so I would write that as minus 270. But this one's far away from the y-axis. This one is closer. So you choose the one that gives you a positive curve closest to the y-axis. So this is a negative 90 phase shift, so I'm going to write it as plus 90 in my equation. Make sense? So that is the final answer. And again, if we wanted to write the cosine name of this curve, we could, but John doesn't ask us for this time. All right, that is a phase shift. That is when we have made our curve out of yarn, and we have glued it so it's stiff, and we can lift it up and move it to different places on our grid and measure how far we moved it from that y-axis. Now we're going to go to part B and talk about a different kind of change, which is talking about the period of a sinusoid. And that has to do with how quickly it repeats itself. So let me just draw you a couple really simple examples of this. 1, 2, 3, 4. We're not going to talk about phase shifts in these pictures. Okay, so our basic sine curve looks like this, right? Every 90 degrees, right? This is 90, 180, 270, 360, plus 90, what is it? 450. Okay, and then this is minus 90, and it goes on, right? This is the period of a sine curve. But what if the curves were tighter? What if it repeated its cycle in just 180, right? What if it was just tighter, like that? See how the green is more stretched out and the blue is more squished together? And then we can do it the other way too. What if, instead of completing its cycle in 360, what if it only did half of it in 360? And then let me just extend this. And then it needed, right? What if it was like that, where it was stretched out? So we can take the curve, and these somehow I imagine them being made of pipe cleaners. We can squish them, or we can pull them apart to make the loops in the curve, if you will, tighter or looser. And the way we measure what we call a period is to go from peak to peak. Okay? So in our normal sinus curves, sinusoid curves, whether it's sine or cosine, normally we measure from top to top. It is 360 degrees is the quote-unquote normal period. That's what we've been looking at. But we can make them smaller periods or longer periods. And let me just show you. A second, I'm cutting through John's. This blue one, let me switch to my blue marker so you're clear on what I'm doing. To show this in our formulas, we would write this as y equals, let's see, we were calling this the sine. We put a number in front of the argument. Okay, so if this first one was y equals the sine of theta, that's our normal. 2 theta means that the period is 2 times, or it's 360 divided by 2. We'll get to that in just a minute, how you calculate how long the period is. And then this one, we would write this as y equals the sine of theta over 2, okay? So a coefficient greater than 1 means the curves are tighter. If the coefficient is a fraction, it means the curves are looser, okay? And we're gonna get into how exactly you calculate those in just a minute. Got so many pens in my hand, I don't know what I'm doing. All right, here is the way you calculate the coefficient. Okay, so we know it's a coefficient in front or below of the theta that helps us determine the size of the period. To calculate the coefficient, we take 360 divided by the actual length of the period in degrees. Okay, so in this one we said we were going twice as fast, so instead of 360 it would be 180. So when we do this calculation, we would have done 360 over 180 equals 2, and that's where I got that number. Let me just write it. It's 360 divided by 180. Okay. For this one, it was 360, but we needed 720 degrees to do the whole thing. So that's where I got essentially the 1/2 that gives us the 2 on the bottom. All right. So this is the little formula that we can use to calculate what that coefficient should be. Now, just to throw your brain into further turmoil, sometimes we're going to use radians to measure these. So this is pretty much common sense. If we're measuring in radians, then instead of dividing 360 by the period, you divide 2 pi, because that's a full circle for radians, right? So now we know how to do it in either unit. And now we'll practice that, okay? And we just have 2 more of these. Again, sometimes I draw the sinusoid out for you in the teaching, because that way I can write on it and talk about it a little bit more. But you do not need to do that for the homework. And honestly, I think it adds frustration because some of the details are quite fussy. It's much easier to just look at it in your book and think it through from there. So I do not recommend that you copy them. It's a little bit too much trouble, to be honest with you. Okay, let's look. Write the equation of the curve. Okay, well, we can assume it's a sine curve. John doesn't tell us that, but it comes very nicely out of the origin at the right place for a sine curve. So let's call it a sine curve. We can see there's a center line of 10, and then it goes 2 up and 2 down. So it's going to be 10 plus, here. Let me cover up the answer. Oh. So it's going to be 10 plus, get my book here. Okay, write the equation of the curve. Y equals 10 is the center line, plus 2 times the sine. And now we see John's being kind. We do not have a phase shift in this one. We just have a period. So we can see, let's see, we measure from the top to the top and we look to see how many degrees that is. John doesn't really have the right measures for us. So I'm going to measure from the rising point to the rising point. So you just have to find the same point in the cycle and measure from that. So I'm going to measure from here is 0, from this one is 90. So it looks like we do our full circle in 90. So the coefficient will be equal to 360 divided by the period in degrees, which is 90. Right? And that equals 4. So it's 4 times theta. That's our final answer. And look, there it is. That's right. Let me show you. John agrees with us. Yay. Beautiful. Okay, that's how I recommend you do it for your homework. Don't try to copy that whole diagram. It's too much work. Okay, and then here's example 57.4. Write the equation of the given curve. Again, we use common sense. Looks like it's a nice cosine curve. Its center line is minus 10. Plus 3, right? That's the difference between the center line and the extreme points. So it's going to be 3 times, and we said it was cosine. We don't have to worry about a phase shift. John's just giving us one thing at a time. And we know there's going to need to be a coefficient on that theta. Let's look and see how long does it take it to do a full rotation. Oh boy, John did this one in radians. That's okay, we can manage this. Pi is half of a circle, right? Okay, well, we don't even need to convert it into degrees. We can just see, though, that that's pi, that's half a circle. It completes its cycle in half a circle, so the coefficient will be equal to 2 pi divided by the actual period, which is 1 pi. So the coefficient equals 2. There. Minus 10 plus 3 times cosine. John does not put the argument in parentheses. I guess I'm okay with that. I wouldn't be mad if you wrote your argument like so. For a phase shift, you absolutely have to put it in parentheses. For a period, I guess it's okay if you write it like that, but I like that better. All right, that takes us through to the problem set. If you feel a little bit wobbly on these right now, trust me, they will get to be more familiar as you go on, and most students find these delightful and fun and a nice little challenge once you get the hang of them a little bit more. Okay? Yay, lesson 57. Thank you, goodbye.